Hello, welcome to Fundamentals of Acoustics. Today is the last day of this course, and today we want to cover some brief topics which are important from the standpoint of applications. So, the first topic I am going to discuss is NRC. So, what is NRC? It is an acronym for noise reduction coefficient. So, what is the context? Suppose you go to a market and you say that I want some tiles for a room, and these tiles should have good sound absorption properties. So, the shopkeeper will go back and look at his store, and let us say he gives you this kind of a tile which is shown here. Okay. So, he gives you this tile and you say how good this tile is in terms of reducing noise. So, he will say okay, I will give you the NRC data for this. So, what is NRC? He will give you some numbers and those numbers will look something like this. So, he will give you for different frequencies 200 and it goes on till. So, these are all central frequencies and the next frequency will be 200 times 2 to the power of 1 by 3. So, these are central frequencies for 1/3 octave bands. Okay. So, he will give you for 200, then 200 times 2 to the power of 1 by 3 and so on and so forth. So, it will go up to 5,000. And for each frequency he will give you a NRC, noise reduction coefficient, and he will say this is 0.08, 1, 0.2, so 0.1 and so on and so forth, and here may be 0.4, and then he will also give an overall NRC value which will be some sort of an average for all these values, and that will be maybe 0.35. So, using these data, so this is noise reduction coefficient and this is for that particular tile or that material which you are purchasing from the store to build your room or auditorium or whatever. So, based on this NRC data you can compare different materials, and it is important, especially if you are constructing a room or an auditorium or a theater where acoustical properties of the room are important. So, in that context, understanding what is NRC and then using NRC parameters to compare different sound absorbing materials is important. By the way, for windows, when the window is open, what is the NRC for that? NRC equals, it does not absorb, it does not reflect any energy, whatever energy goes it just goes out. So, NRC is equal to 1, and for rigid surface NRC equals 0, all the energy gets reflected back. So, that is the first topic for discussion. The second topic is reverberation room. Reverberation room. Okay. So, what is a reverberation room? I will show you a picture first. So, first we will describe what is a reverberation room. It is a room designed to create diffuse or random incidence sound field. So, first thing, sound field. So, which means that at every point in the room the pressure is same, because there are reflections happening all over the place. See, in a rectangular room, you have standing waves in a rectangular room. So, at some point pressure will be high and at some point pressure will be low. For instance, as wave travels through a closed tube, at some locations you have a standing wave in a closed tube, and at some locations the amplitude of pressure is very high, at other locations the amplitude of the pressure is theoretically 0. But so the absolute magnitude of pressure changes if I change the position. In a reverberation room, what we want is that at every point in the room, the amplitude of the pressure should not be changing. So, how do we acquire it? First thing is that standing waves tends to develop in rectangular rooms. So, we make rooms which are not rectangular in nature. So, they may have angular walls and things like that. So, because of that, standing waves do not tend to develop easily in such rooms. So, that is one thing. The second thing is, so you see this room, this is a picture of a reverberation room. So, this surface and all these walls are rigid surfaces. So, when sound comes here, it gets reflected easily and does not get absorbed a lot. And then all these angles are not necessarily at 90 degrees. So, standing waves do not tend to develop easily. And the third thing what they do additionally is that if sound is going here, you put an additional reflecting surface here. These are transparent reflecting surfaces and they are also somewhat rigid. So, when sound comes here, it does not get a chance to hit here, it reflects, it hits this curved surface. So, sound bounces off in all directions and as a consequence sound pressure uniformly gets distributed in the whole room, So, that is the attribute of a good reverberation room, that if the sound field at different points in the room is diffuse and it is not like that of a standing wave. So, in these kind of rooms, what is the sound field? We have discussed this earlier, it is a diffuse sound field or a random incidence sound field, right, because sound is coming at every point from all directions. So, surfaces of reverberation rooms are very hard in nature, and what do we use these reverberation rooms? So, suppose I have an absorption, a material with unknown absorption coefficient, I can use a reverb room to compute its absorption coefficient. How do I do that? So, first what I do is I go to the room and I do not put any absorbing material and I will get its reverberation time, right. I can measure its reverberation time and I know the volume of the room, I know C. So, from that I can compute A prime. The next thing is, so once I know A prime, I can also calculate alpha bar of the room. Okay. So, this is the first step. Step 1, measure T1 using microphones. So, when you are doing the recording, initially the pressure in the room will be high and slowly it will decay. The time it takes for the sound pressure level to decay by a factor, by the sound energy to decay by a factor of 60 decibels, that corresponds to the reverberation time. So, reverberation time T1 gets measured, we already know V of the room, we know C. So, from that I can calculate alpha prime. Once I have alpha prime, I use this relation and from this alpha prime, S is the surface area of the room, that again can be measured. So, from that I can calculate alpha bar, which is the absorption coefficient of the room. For a reverberation time room, it will be very small. Okay. Now, what I do is I put an sound absorbing material on some wall somewhere in the room, and once I put that, the absorption coefficient of the room will change. Okay. So, initial absorption coefficient is alpha bar and it is this number, right, it is this number. If I put an extra material, then what is this? The new absorption coefficient will be alpha prime, which will be all the initial components plus alpha of the unknown material times its area divided by S, agreed. So, if I can find now alpha prime for the room, then from that I can back calculate alpha u, which is the sound absorption coefficient. So, how I do that? I once again now again measure the reverberation time of the room with the absorption coefficient, and in this relation from T2 I compute the new, which is the modified parameter A, and this parameter A is log of S prime times log of 1 minus alpha prime. So, alpha prime can be recalculated, and in this equation I know the left side, I know all the terms on the right side except alpha u. So, I can go back and measure the absorption coefficient of the unknown material, and this absorption coefficient will be for a particular frequency. So, I have to do this experiment for several frequencies and then I can characterize the material. So, with this we can use a reverberation room to characterize materials with unknown absorption coefficients. So, these were the two important topics which I wanted to discuss today, and with this we conclude our discussion for this course. What we have done over this entire course is a series of things. We started discussing in this course by making some introductory comments. Then we introduced you to important mathematical concepts which have been frequently used in this course, and then we went on and discussed the one dimensional wave equation, solved the one dimensional wave equation, used this one dimensional wave equation's solution and associated transmission line equations to make important observations about standing waves and waves which are travelling freely. And then we went ahead and explored the idea of impedance both for radial waves as well as planar waves, and we also described the Kunz tube apparatus which can be used to measure the impedance of a material. And after that we came to the area of applications, and from the standpoint of applications we touched upon a variety of topics, starting with mufflers, how to measure impedance of an unknown material, how do radial waves propagate and what do they physically imply, and a slew of several other topics. So, I hope this course, which is introductory in nature, has been of benefit to both people who are studying in colleges and universities as well as to people in the industry. And please feel free to ask questions if you have to the TAs or to me, and I think next week or a few days from today you will be having your final examination. So, please study well for a final examination. It will be a multiple choice type of an examination, and I hope you do good in the exam. So, thank you and best wishes for the future. Bye.